Good afternoon, ladies and gentlemen. My name is Benny. I have been tasked by GPC local municipality in South Africa to develop for them a water distribution network. I have been tasked to find out whether the township demand is given for each township 1 up to township 4, can be met by drawing water from the Jangwe River. The 5 townships are located such that all of them are on the same side of the river, but between the township there is a hill, which is an ideal place where I will position the bulk storage tank. This is the layout of the township. Given the reduced levels, whereby the level at the river is the datum, that's a 0. So reducing all the levels of the nodes and the demand centers, as well as the junctions, I work out the elevations of each and every node. And these elevations will be used to enter as the input data in the Ethernet design software. What is required also from me is to come up with the correct pipe sizes, the diameters of the pipes. That's very important because you cannot just put in any diameter pipe because you want water or because you want to meet the demand, because there are some factors that needs to be looked into, like bigger the pipe might be expensive, or there will be head losses, too much head losses, or there can be reduced flow. So there must be sufficient flow, and also the velocity of the pipe must be maintained between 0.6 meters per second and 1.5 meters per second. That helps a lot, because if the velocity is too low, then there is not going to be sufficient flow. And if the velocity is too high, it causes scouring of the valves and some of the fittings that are inside the pipe. And also, if you maintain an adequate velocity between the minimum of 0.6 meters per second and 1.5 meters per second, these values are taken from the guidelines and the literature that I have reviewed. So then if you stay within these ranges, then you also protect your pipe systems from what is known as hammerhead and so on. And also from the literature review, it's also required that at least at the demand, the head shouldn't be less than 20 meters. And at the bulk storage, there must be a constant supply, because one of the requirements is that the reservoir should have sufficient capacity to maintain 8-hour supply without being pumped. The known data is that, as I've mentioned earlier, the reservoir must be able to supply water for 8 hours without being pumped. The cycle must run for 3 days, 72 hours, and the pumps should have the capacity to pump 600 liters per second at 8-meter head. That 8-meter head is a good parameter, because if the elevations that I have worked out, the elevation of the bulk storage, which is the highest component, sits at 74 meters. So it is less than the 8-meter head given for the pump. So the pumps will be capable of pumping up water into the storage tank. Each township has got a demand. For example, township 1 has got 60 liters per second, township 2, 75 liters per second, 3, 85 liters per second, and 4, 325. But this demand is given in terms of liters per second. But now we have converted those values from liters per second and multiplied that by the 8-hour that's required for the storage tank to have that capacity without being pumped. And the required storage is 10,224 cubic meters. So given the dimensions of the diameter, 12 meter high, 34 diameter, it gives me 10,895 cubic, which is more than the required demand. In pipe systems, there are always losses, either real losses, sometimes losses known as minor and major losses. But these losses are not due to pipe being breaking apart or pipe burst and so on. Depending on the material that has been used to manufacture the pipe, whether it's a plastic pipe, cast iron pipe, or concrete pipe, the inside of the pipe, the internal wall, has got some defects or deficiencies, which is called as, it can be either rough or smooth. The rougher the pipe, then the liquid that flows, in this case, the water that flows loses energy, and we do not get the enough, does not meet the demand at the end. So now this Ethernet software that I'm using makes use of the Hudson-Williams head loss formula, which is an equation for calculating head loss in pipes due to friction, and it relates flow of water in pipe with physical properties of the pipe. And just for information, I'm going to be using 145 as the roughness value. Then to start, I have the layout that I have shown you earlier. I have drawn it on the internet, and that's exactly similar to what the schematic view that I have given you earlier. Then I have put in, for the performance capabilities of the pumps, the given data that was 600 liters per second, and it must pump at a 80-meter head. And that is the pump curve. I will be using two pumps, one pump to pump water from the river up into the water treatment plant, and other pump takes the water into the bulk storage tank. And this is just a schematic and illustration from the Ethernet drawing to show that along the pipelines you can see the various diameters. For example, in this case, for this pipe here is a diameter 450, 450, 450, there's 600, 450, 1000, and 1050. But these were trial and errors, because in these diameters I was playing with them, but always keeping in mind that I must have design velocity ranging between minimum of 0.6 meters per second to a maximum of 1.5 second. And that curving has taken me to the successful run. And successful run on Ethernet, I have now my pipes numbered. The pipe number 2 and pipe number 4 are pumping mains, because they are this pump wants to pump water up to here, and that pump will pump water up to the bulk storage tank. But those green ones are the gravity mains, because here this bulk storage tank is situated on top of a hill, and water will flow down by the force of gravity. And looking at the legends, let's look at this one for demand. Demand is related to what is required at the nodes as well as at the townships. So looking at the color, these two, demand center 1 and demand center 2, gives me slightly a bluish color. And it says that the demand is more than 25 meters up to 50 meters. So it's within, it's fine. And dark blue is also just about 20 meters. And the yellow, that demand center 4, sits at a demand of 75. But that's not the demand that we are designing for. That's just an indication of where the demand is lying. Looking at the velocities, green. All gravity mains are green. So their velocities are more than 0.6 meters per second and less than 1.5 meters per second. There is now pipe having a color of red. A red takes you above more than 2 meters per second. This table only shows us the roughness, as I've indicated earlier, the velocities. For example, the velocity of pipe number 2 here, which is having a diameter of 1050 millimeters, sits at 1.18. So it's within, it meets the demand. Now we look at what is the situation if water is being pumped from the water treatment plant into the bulk storage tank. Here on this graph, you can see two lines. The green that runs on top starts at the bottom, slightly at the bottom, in the middle, and runs towards the top, and the red that starts right on top and comes downwards. What it means is that by the time the treatment plan starts, the red line, then it starts pumping just about 600 liters per second. And at that state, that's now when that cycle has started after 72 hours, the reservoir already is sitting at the demand of 200 liters per second. So the treatment plan can meet it because treatment plan is velocity higher. Within about 5 hours from the start, excuse me, it breaks even, but as you can see, the green line, which represents the bulk storage, then keeps on rising and rising, meaning it meets the demand right up to the 72 hours. And the treatment plan, as it is pumping up more water, it's coming down, but in the 72-hour cycle, it goes back and starts all over again. Then we've got another bulk storage tank compared with all 5 demand centers. In this case, the red line right on top is never below the head in meters of the 4 townships that we're given. That is an indication that the demand or the head of these townships, township 1, 2, 3, and 4, is met since the bulk storage tank demand is higher than all as indicated. So it's a successful design. But there are also challenges when we are designing. In this screenshot, I'm going to show you what happens when, for example, you play with the sizes of the pipes, trying to get the specific or the required diameter, trying to keep the velocity within the given parameters. But as you can see at demand center 1 and demand center 2, it does not have that red color, meaning the velocities here are just at the border, just below 0.6 meters per second. So, which is not a good thing. So in this case, it only indicates that we've got a positive pressure at demand center 1 and demand center 2, which is a good thing, because if there was a negative pressure, we play around with the diameters, but we were restricted to have a minimum diameter of 300 millimeter pipe. And this pipe sits has a 305 millimeter and that one at 315 millimeter. But these are some of the challenges that one picks up from the software and from the given input, and then one needs to work on that. Conclusion, the required velocities, all these parameters are based on the literature review, like the Red Book, Human Settlement, Planning and Design, which gives that the flow velocity must be within a certain parameters, that the demand at the end, where before it gets to the user, must be at a certain height, like for example, shouldn't be less than 20 meters, and that the pumps must have the sufficient capability to pump water. In this report, we found out that the 2 pumps are working at the efficiency of 75%. So hence, I would recommend that the municipality may go ahead and implement the water distribution model as explained. Thank you so much.